Right, last recording, we looked at particles exhibiting wave behavior, and we looked at some examples of waves exhibiting particle behavior as well. So, using that idea, we are going to answer this question here. I did go over a very, very similar example, which was example 2 on calculating the wavelength of an accelerated electron. So this is very similar. By what factor does an electron have a larger wavelength if both an electron and a proton are accelerated within a PD of 80 volts from rest? Now, if you note that my previous question from the end of last video, this here was proton. All I've done is change it into an electron. Doesn't make a difference for majority of the calculation, as you'll see. So the first part, we're looking at calculating the de Broglie wavelength of a proton which is accelerated within a PD of 80 volts. So a proton, a particle, is moving after it's been accelerated at a finite speed. After it has completely sped up, what speed would it be? We will work that out first, and then using that speed, we will use de Broglie's wavelength formula and work out this wavelength. So on the left here, I've drawn a picture. We have got, let's say, two plates, and you've got a proton sitting at one end, close to the negative plate, and a positive. Sorry, got this wrong way around, so let me just change it. So you've got a negative here on this side, and a positive there. Right, okay. Now, let's go back. So you've got a proton accelerating towards the negative plate. The potential difference between the plates is 80 volts. We need to look at energy changes. So we've got potential energy between the two plates, electric potential energy, which is the charge times by the voltage. And all of that is converting into kinetic energy, which is half mv squared. So because it's a proton, we are looking at the charge of a proton. The voltage between these plates is 80 volts as given to you in the question. The mass of a proton is on your data sheet at 1.67 times 10 to the minus 27, and that will enable us to work out the velocity. Rearranging this to get V equals gives us this expression. Putting the numbers in, where this is the charge of the electron, that's the voltage between the plates, and that is the mass of, sorry, not the electron, the mass of the proton. So what we've got is a speed. Once it's completely accelerated between 80 volts, it will have a speed of 1.24 times 10 to the 5 meters per second. You'll be expected to do this calculation in your exams. Often the next part of the exam question is working out the wavelength. So we've got this speed this proton is moving at. We can then work out the momentum and then the de Broglie wavelength. So the momentum is the mass of the proton times by the speed of the proton, and it's the Planck constant divided by the momentum, which is this de Broglie wavelength. So when this proton is accelerating and moving at this speed, it has a de Broglie wavelength of 3.18 times 10 to the minus 12 meters. So this particle has a wavelength of 3.18 times 10 to the minus 12 meters. Similarly, I'm going to do the same thing for an electron accelerating within a PD of 80 volts. This time I've got the speed that I've worked out to equal 5.3 times 10 to the 6. So the electron's accelerated, is gained speed. How much speed has it gained? 5.3 times 10 to the 6 meters per second. Because an electron has a mass, it has a momentum, and we can use the same de Broglie wavelength to work out the the wavelength of the electron. So 9.11 times 10 to the minus 31 is the mass of the electron. The speed of the electron after it's been accelerated by 80 volts is 5.3 times 10 to the 6. And what we've got is the de Broglie wavelength for the electron is 1.37 times 10 to the minus 10 meters. Now, my question was compare the de Broglie wavelength for the electron and the de Broglie wavelength for the proton. And I had it the wrong way around. I should have the other way around. So my initial question was the de Broglie wavelength of the proton over the electron. I'll just do it, the electron over the proton. So the de Broglie wavelength of the electron is 1.37 times 10 to the minus 10, and the de Broglie wavelength for the proton is 3.18 times 10 to the minus 12. Now, that shows us that the de Broglie wavelength for the electron is 43 times larger. So the reason why we use electrons in microscopes and in the electron microscope is because the wavelength is comparable to the gaps between atoms. Now, the gap between an atom is in the order of 10 to the minus 10, and the electron shows us that wavelength, whereas the proton is about 100 times smaller. So the proton's not going to show wave behavior as it passes through the gaps between atoms of different molecules and compounds. Now, you've worked out the wavelengths of the electron and the wavelengths of the proton by first working out the speed and then working out the wavelength. So, two-step process. In your exam, that's the kind of questions you will get, but there is a very small chance that you will link voltage directly to wavelength. So the 80 volts the electron accelerated through directly linked to the wavelength. So let's have a look at that. So what I'm going to do is I'm going to look at the expression of electric potential energy. So between the plates, it was 80 volts. All of that was converted into kinetic energy. Now, as an expression, the electric potential energy is charge times voltage, and the kinetic energy that the particle would have gained was a half mv squared. So I can write that down as a equal sign because all of the electric potential energy converted into kinetic energy, that's the final speed of the electron once it gets to the other side of the plates. Right. So what I'm going to show is a quick trick here, and in the end it will become more apparent of what I've just done. So what I'm going to do is I'm going to multiply both sides by velocity. So some algebra here. So I'm timesing both sides by velocity. Actually, tell a lie, that's wrong. I'm multiplying both sides by mass. Okay, now if I multiply both sides by mass, what I get is mqv, that's the voltage V, equals a half m squared v squared. Now that's the same as writing mqv equals a half mv all squared. We know that momentum P is equal to mv. And now I'm going to substitute that into this equation here. And what we end up is mqv equals a half momentum squared. Okay, now I'm going to rearrange to get momentum equals. So the momentum equals 2mqv square rooted. Okay, now when we go and look at de Broglie's wavelength is Planck constant divided by P. If I substitute this expression that I've just worked out, so I get 2mqv, and that's the voltage V, as the factors at the bottom. So here we are, and we can see that the de Broglie wavelength is dependent on the mass of the particle that's been accelerated, the charge of the particle, and the voltage that the particle has been accelerated between. It has to be a charged particle for it to be accelerated. So when I asked you the question, which will have a larger de Broglie wavelength if it was accelerated between the same 80 volts? Now, a proton and an electron have the same magnitude of charge of 1.6 times 10 to the minus 19. The potential difference from what I asked you within the question, they were the same. So the only factor that was affecting the de Broglie wavelength was the mass, because everything else in this expression is constant. So the larger the mass, the lower the wavelength. Now, let's go back and just confirm it. So we've got an electron that has a small mass compared to the proton, yet the proton has a smaller wavelength, and we can now see that's definitely the case. So if you wanted to create a set of ratios to answer my question of the wavelength of the electron over the wavelength of the proton, you could have rearranged this equation and written mass of the electron times by the charge of the electron over the voltage that the electron is accelerated between, over h, the mass of the electron, mass of the proton, times the charge of the proton, times by the voltage that the proton has been accelerated through. And we know that from the question I asked that the voltage was the same, the charges are essentially the same. Planck's constant is Planck's constant. So what we've got is here the mass of the electron and proton define the wavelength, and what you'll end up with, most of these variables cancel, and it's the wavelength of the electron over the wavelength of the proton is equal to the mass of the proton over the mass of the electron, all square rooted. Now have a go at that you should be able to do as well. I've jumped a couple of steps to go from there to there. That's algebra, which expect all of you to be able to do.